Awesome. Hello, everyone. Thank you, Annie, for the introduction panel, the pros and cons of ZK coprocessors. We're here joined by a number of high-profile individuals that are all to the aspects of coprocessing. We have here Scott, the CTO of Space and Time. We have Michael, the co-founder of Brevis. We have Stephen, the head of strategy at Risc. And we have Ayush, the co-founder of LayerEdge. I guess to give a context of ZK coprocessing, it is a critical element in enhancing blockchain performance and comes with unique challenges for complexity, compatibility, and managing these increased costs. We'll be exploring the implications of adopting coprocessors, their benefits, and their trade-offs. So I guess to start off the panel, what are the primary advantages of using ZK coprocessors in blockchain infrastructure, and how do they impact overall scalability and efficiency? We'll start off with Scott.
Sure, great to be here. Excited to see some familiar faces. ZK coprocessors offer a way for smart contracts to kind of offload a lot of computations that they either can't do on chain, like technically can't, or where the gas is too complex to do on chain. And furthermore, it allows those computations to be executed against historical state from the chain, right? Like most smart contract developers are often a little shocked when they get into smart contracts and realize smart contracts have no access to like historical blocks and ask complex questions about historical activity on chain. So the up and coming ZK coprocessor space offers a solution to allow those computations to be done next to the chain and then proven back to smart contracts that need those computations.
Well, that is a great answer. I think that summarizes up a lot of what coprocessor does. I just want to provide a perspective in terms of like the trade-off dimension, the trade-off space, and how we evolved from the early stage of layer 1 blockchain all the way to coprocessor. Right, so in the early days, if you look at the layer 1 blockchain, we only have 3 dimensions in the trade-off space: decentralization, security, and scalability. Right, so what Ethereum chose was obviously high decentralization and high security with pretty poor scalability. Now we have better scalability in the Ethereum ecosystem because we have layer 2. What are layer 2s? Well, layer 2s are essentially introducing an additional dimension in the trade-off space to make the trade-off space from 3-dimensional to 4-dimensional. That 4th dimension here is unity, or unification of states and liquidity. So what rollup did is to trade off or significantly reduce the liquidity unification and user unification and improve performance that way. So we have better performance on rollups, same level of security and decentralization, but much worse unity with liquidity fragmentation and user fragmentation. Right, so however, if we look at performance, it is still not enough. Like as Scott rightfully pointed out, there are still a lot of type of computation, things like access historical states and do the computation on top of that. That is very hard to do even on layer 2 rollups. So this is why we need to play the trade-off game again by introducing yet another dimension of the trade-off playing space. And this time we introduced the synchrony. That we introduced an asynchronous architecture to allow blockchain to offload computation to an off-chain environment in an asynchronous way, and then bring the result back, so that we can have infinite level of scalability, but at the same time, 0 fragmentation of user liquidity and everything. So I would say this is how I view the evolution of coprocessors.
Yeah, I mean that's a very comprehensive answer. I don't think there's much else to add other than something that really excites me about coprocessors is what they mean for developer expressivity. Because at the end of the day, whether you're on a rollup or even a super high performant thing like Solana or Monad, you're building in environments like EVM and SVM. And naturally, those are extremely restrictive and really limit what developers can do. A lot of the ZK coprocessors that our team is really focused on, because they're grounded in a ZK VM, allow developers to build in Rust. And we've actually seen this be a really big thing in terms of what it enables developers to do, whether they want to build order books now with fully Rust-based matching engines, basically we've seen a substantial improvement in like what applications can functionally do because of this new developer interface.
Yeah, so I think all of the everyone has actually completed like what advantages that we can get from like the group processing. Like I can only add like the point that like it actually enables like a lot more like aspects of things that were initially not possible in the very decentralized way. For example, if we ever want to now, like in our case, we are creating aggregation. So like if we do all the computation, say on chain, it's like nearly like impossible for us to do. But like with the help of coprocessors, like it can be done in a fast and efficient way. And like along with that, like a lot of things, like for example, if you want to give any VIP points or any, like there are a lot of new use cases that have been enabled by processors. So I'm like pretty like bullish on like those type of things because that can actually move like DeFi from a like a plainly like the vanilla DeFi that we currently have to like more of a like real world financial institution, like assets and like mechanics we can implement.
Perfect. I think the overall theme is taking the historical data and taking data that's inaccessible within the blockchain context or just too expensive, taking that off chain and then bringing that back on chain essentially as a way and a means to compute off of that data. And so essentially taking the stuff that's complex, bringing it off chain, then putting it back on chain in a verifiable manner. And I guess, can you, I think I actually missed this in terms of introductions. Can you also introduce yourselves and say specifically how your project is operating within the ZK coprocessor space and anything that you're currently focused on in that way? And then I guess we can start with Ayush, if
Sure. So like what we are basically trying to do is to create like bring aggregation to like the Bitcoin space, because in Bitcoin space like right now everyone is trying to do the native verifications on Bitcoin with like one of n trust assumptions. So like this is very good, but the main problem with everything is like it's pretty expensive. Like right now if you see it's like close to like $900 per block. So what we are trying to do is to create aggregation layer for all the ZK chains and protocols, and for creating the aggregated proofs, like we are using like ZK processors for like creating the aggregated like Merkle tree and like doing like the recursive proof generation so that we can come up to like a root node.
Yeah, what we're building at Risc is a ZK VM, and that principally makes ZK development substantially more accessible and performant. All of this is being based around Rust-based development. And then what we're doing with the ZK VM is then connecting it back on chain using our protocol called Boundless. And what this enables is this ZK application stack that very much mirrors coprocessor-based architectures where the majority of compute is moved off-chain. That's really what our mission is at this point. Basically, how can we take all the on-chain compute and move it off-chain? We think with the performance of ZK, with things like aggregation and other mechanisms, we can get to a point where a lot of the logic of applications can be fully ported into ZK.
Yeah, so at Brevis, we build off-chain verifiable computing, in the coprocessor architecture. Now, there are many different kind of a product on the roadmap, but the first product we launched is a ZK data coprocessor that focuses on offloading, data access and computing, historical data access and computing type of computation from an on-chain environment to an off-chain environment. And with that, you can essentially build application that is driven by historical state and behavior of your protocol, of your user, and differentiating user experiences, and do many things like that. Our solution is we try to kind of find the optimal trade-off point between performance and also programmability. So we offer an SDK that is highly programmable for developers to express their business logic using different type of data stream APIs. But at the same time, for the specific use case of on-chain historical data access, we provide extreme, fast ZK proving engine to do that. So yeah.
Scott Dykstra, co-founder of Space and Time. Space and Time is a ZK coprocessor specifically for SQL against indexed chain data. So one thing that's unique about Space and Time compared to most ZK coprocessors is that we're not building a ZK VM, we don't support arbitrary computations, and we don't we actually transform the data a little bit before loading it into the processor. We actually kind of build almost like a Dune-style data model of Ethereum data and Bitcoin data and a number of other chains that we've indexed. But then we allow smart contracts asynchronously to query all that on-chain activity with SQL. And so we spent about 3 years just building the fastest frickin' ZK coprocessor we possibly could, just hyper-focused on SQL against blockchain data.
Awesome. I see like a various different types of directions in this space, well, from generalizability to specifically based on you know, the blockchain. So for Ayush's Bitcoin, for Risc Zero, for generalizable ZKVM, and then like for Brevis it'd be specific like SDK for the development, and then we see for Space and Time we have the highly performant and indexable SQL-based ways. So there's different methodologies for that to getting performant optimizations or generalizable depending on the flavor of the co-processing that you're looking for. And I guess like on that note, in terms of the biggest challenges associated with integrating the co-processor in terms of data, I guess we'll start off with Scott again, and you know, what were the biggest challenges for that type of integration with that to occur to be performant? Like, what was the design considerations for that?
Yeah, good question. And this panel is the pros and cons, so I'll talk about the cons in that context. I think one of the biggest challenges of coprocessors in general is the asynchronous nature, and you called this out well too. The problem that we all have is smart contracts will get their answer back, like the result of some computations that are executed off-chain in a coprocessor, or a query result, or you know, the output of some DeFi calculation executed in Risc Zero. Like, they'll get that answer, that output back in later blocks. And the problem then is there's additional gas that's paid usually by the coprocessor themselves to verify proofs on chain. So there's gas for the verification, and then there's gas for the transaction to asynchronously submit the answer back on chain to the smart contract that requested it. Oracles like Chainlink had the same problem during DeFi summer in 2020-ish, right? The asynchronous nature of calling an oracle, passing a payment, getting back an answer later. And that slows down transactions if the co-processing needs to occur during a transaction. A lot of the coolest use cases that are already popular are more asynchronous by nature, like use cases that don't require an answer back next block. Where there's no hurry. Hey, you have a big processing job where I don't want to pay on-chain gas for the actual computations, and it can run for as long as you need. Just give me back the answer sometime in the next hour, and that'll make some decisions like rebalancing a pool, or some governance decisions, or, you know, maybe rewarding node operators or something where it can just happen once a day. No problem. But for transactions that need to kind of get their answer back quickly, the asynchronous nature can be challenging.
Yeah, I mean, like, I definitely agree. This is definitely the biggest kind of a pattern change in terms of developer experience and developer, you know, kind of a build how developer can use ZK coprocessors. But just like any kind of a trade-off space, you know, games that we have played in the last, you know, 50 years in computer science history, there's always a way to just add another layer of abstraction and try to mitigate that. Right, so like, you know, we had this kind of a similar problem in Web 2, actually, in the early 2000s. So the entire web architecture, like internet website architecture, was very much rooted in a synchronous architecture back then. You have one server that handles everything: authentication, data storage, computation, everything. So that was super slow, and internet, you know, user grow like rapidly, and that architecture couldn't handle that. This is where we actually introduced this type of asynchronous web architecture, where you have a web server now, like Nginx and you know, all the popular web servers are just acting as a glue for many back-end kind of you know, specialized co-processors the things like AI, things like data processing and everything, right? So, the way that people can mitigate this challenge is by providing developer with an illusion or abstraction of synchrony. So like, even though that underlying what happens is there's a message sent out and then, something goes back, but today's web development architecture doesn't actually expose the raw asynchrony to the end developers. Developers themselves are just writing functions, they understand the basic concept, but they don't need to handle the messages, send a message and everything. So that's where we think, the ZK coprocessor space will also go by providing better abstraction, better user, developer tooling to mitigate that kind of a, fundamental challenge there.
Some architecture that we've recently seen that I think excites me, and also kind of gets around the async issue, is taking the application as a whole and moving it off-chain. We're seeing this with kind of what it's called provable exchanges or provable applications. In this case, like the order book fully runs off-chain effectively in a server in their office. And then every hour or so, all of the bids and asks and the order matching algorithm as well are processed through ZK and submitted onto Ethereum or onto Arbitrum. And basically what you get there for the user is a Binance-like, sub-millisecond bid ask order matching experience. And then the only thing that lags behind is this sort of hard finality, which is dictated by the ZK proof itself. So basically, instead of having to try to sync up with Ethereum or whatever chain after every single proof, you kind of let the application run by itself, and then the ZK just creates like a hard finality checkpoint every once in a while. But obviously, you do lose a lot of trust guarantees with this, right? There's censorship, there's a lack of decentralization, which can be fixed in different ways using traditional distributed systems. But it's a cool architecture, and I think for the developer, they built the order book like Binance would have built it. They didn't have to think about async anything. The only thing they had to build on-chain was a sort of deposit withdrawal mechanism, which is relatively standardized across most rollups. But in this case, they don't have to deal with blocks or sequencing or consensus or anything like that.
Yeah, I can add like from a developer perspective, like the architecture is actually good because it allows like a lot of new applications, but there is a problem of like sometimes like learning the architect, like the whole like what you can say, using coprocessor for the first time, because the onboarding experience, like as per like my experience which I had with some of the developers, is like it takes like some times because it is relatively way more different than regular regular development, like for any like what you can say, smart contract developer. So initial learning phase is a little bit rough, but like after that, like the advantage that we actually have is like pretty good. So like as a whole, like as you're saying that you have developed like certain set of like toolings, how like these things can be abstracted out. So with this, like the adoption for the developers would be like pretty huge. But this is a problem that initially like a lot of guys faced.
Perfect. I think definitely different methodologies, being closer to finality and then further away, and then the level of programmability within there as well, like taking into consideration like when do you want the data, how, and then dealing with those asynchronous properties. I guess Ayush, you talked a little bit about the developer experience within these ZK coprocessors. Are there any particular challenges or opportunities that developers need to be aware when building with these technologies, or specifically your tech stack?
Yeah, so like for like the specific coprocessors thing that I found, like the guys who have working with like backend and decentralized systems for a long time, for them it's like relatively easier to grasp compared to the smart contract devs. And like as a whole, this has enabled like a lot of new like opportunities for us. Like for us, like we are basically like focusing much more on the security aspects and the aggregation aspects. So for us, it's like a very good thing because we can easily be able to like create our own like aggregation modules, and then basically settle like a single time on Bitcoin, and then by that we can save a lot of costs. But for that aspect, like it was like a very genius thing, because if we have done it in any other way, we would either like not be able to do it, and the concept of actually abstracting out all the computation and just getting the like verifiable proof at the end of it, which is actually justifying all the transaction, the computations happened, is like phenomenal.
Yeah, two interesting things that we've seen with people building coprocessors is, one, when you're ingesting a lot of state and data, like querying Alchemy for hundreds of thousands of blocks in a minute is actually extremely difficult. And Alchemy themselves don't have really good infrastructure for that. So that's been something we've been tackling with a lot of our partners. And then the second thing being data structures, right? Like on-chain data structures are still really unique, especially because you got to basically Merkleize all your data. And when people are building coprocessors, at least a lot of our partners, they just want to use traditional data structures because that's what makes most sense to them. And then we need to go to them and be like, hey, how do you want to Merkleize like a gigabyte, 10 gigabytes, 100 gigabytes of data every single time you generate this proof? And then somehow submit it on-chain and kind of maintain some sort of connection between your existing database and then your on-chain Merkle root. So a lot of interesting things to play with, and a lot of new ideas that people haven't really touched before, which is kind of exciting. So yeah, basically right now, every single coprocessor partnership we're looking at, they are bumping into something new.
Yeah, definitely. I think one thing I want to kind of add, on top of all that is when you're building coprocessor-based use cases, it's very important to understand and think about what type of data you actually need, right? So there are so many different type of data on blockchain. The most kind of a straightforward one is like states. What is the ownership of an NFT? All the view functions are built based on only just like the Ethereum states. But there are also a lot of information that is not being captured by just the states, such as transactions, raw transaction data, and events, like what is the result of user behavior, right? So these kind of things are sometimes can be extremely useful. For example, if you want to calculate what is the trading volume for a user, you don't need to kind of re-execute the state of every transaction. Instead, you can just look at all the historical events and sum them up, right? So when you're trying to understand and build your business logic, think wider than what's available on-chain as states, but also what's available and emitted as events or the user transactions, interactions, block states, and the con state. All of these things, everything on blockchain is accessible by coprocessor, and in this case, Brevis, provide the widest amount of data available for you to kind of use. So that's something I want to note for the developers.
Our focus is, like I said, SQL, and we're kind of thinking through a lot of real-time use cases where we can run a sub-second ZK proof against, 60 gigabytes of Ethereum transactions or event logs from, a certain DeFi protocol, smart contract events. And we have a lot of customer or partners that come to us that are trying to build more sophisticated DeFi. Think like lending, where the lending protocol looks to see whether the borrower, as they transact, as they take out their loan, see if they've already paid off some loans on chain and give them a better borrow rate if they have. That proof cannot wait very long because the borrower submits a transaction and is waiting for their transaction to get approved, waiting for the loan to be granted to them. And if space and time as an intermediate solution providing the data for that transaction slows down the transaction, that's a frustrating user experience. So we're hyper-focused on how fast can we give this data back to a smart contract verified on chain to give it the context that it needs to facilitate a real-time transaction. I think there'll be much better solutions than space and time for offline processing, like massive and long-running computations that can be verified on chain whenever. Like I said, a minute ago, like examples where there's a proof that's needed like once a day. Like, hey, I'm going to reward my node operators once a day and ask a Brevis or a Risc to calculate the rewards per node. But if a smart contract just needs to know about the user that's borrowing right now, as fast as possible, sum up the total volume of their loans paid off, we're trying to bring that back on chain next block.
really good use cases and definitely, you know, directions for different implementations for developer experience. And it seems like developers are driving, or at least it's use case driven, like for lending, order books, and other means to leverage, you know, the on-chain nature of events. And then in terms of these, in terms of the costs, I would say like costs versus performance. Does your solution, and then I guess this question would apply to everyone. Does your solution optimize more on the speed, on the costs, on the different types of finality guarantees? So like, where are you? Where is your solution leaning towards, and or maybe just extensibility in that case? And I guess we'll start with Scott.
Yeah, we had to make a lot of tough design decisions because depending on what type of commitment you want to use for your data, it might determine how expensive on-chain verification is. And unfortunately, like the design decisions that we made had to balance cheaper on-chain verification at the cost of slower proof times, or vice versa. Speed up proof times, slow down or increase the gas of on-chain verification. Ethereum is tough. We don't really have a great set of curves available as precompiles yet on Ethereum. And so a lot of teams sort of have to make do and make design decisions that usually include folding or recursion prior to verifying on-chain, which then slows down the total round-trip time to get an answer back to a smart contract that needs it. We also made a huge design trade-off on interface, right? Our interface is not Rust, it's SQL. And that's all we're going to support forever. Like we just want to make it really easy to run SQL. And that comes at the cost of some teams can't use space and time because they have you know, a Turing complete need that goes beyond SQL that would require Rust or something.
Yeah, you know, I think one way we look at kind of the cost, you know, profiling is that there are really two ways you can do co-processing in general, right? So like ZK co-processing specifically. You know, one way is you can do everything in ZK end-to-end, you know, all the time. Right, so you know this is what we offer as the first model in Brevis as well. You know, we build an extremely efficient ZK proving core with highly parallel and elastic scaling and everything. Right, so to push down the cost and you know increase performance at the same time. Now, you know, as every computer science problem is a trade-off problem, we can also introduce another dimension in the trade-off equation here by introducing some latency. So the idea here is that you can use something called an optimistic co-processing with ZK fraud proof, that what we offer as a second model in Brevis, where you know the co-processing result will be generated first by a class of a node that is right now running an AVS, and you know without actually computing the whole ZK proof, because this is where the cost you know will come from. So the result will then be posted on chain as a proposal and open a challenge window. During that challenge window, during a challenge latency, if a challenge initiated, you know, you can actually initiate a ZK fraud proof as a challenge to kind of correct the result. You know, this way, you know, for most of the cases, you get a cost to the level of a centralized system that is very, very close to, you know, extremely low cost without any kind of ZK proof cost. But, you know, at the same time, you trade off a bit of latency. So if your use case is not latency sensitive, then you can use this model to get you the same level of security as a ZK-based, pure ZK-based system, but with much, much lower cost.
Yeah, at our team, we're definitely cost sensitive right now because ZK VMs are inherently a lot slower and more expensive than non-ZK VM-based systems. So because of that, we do similarly do optimistic-based models. We do ones where ZK lags behind. But I mean, the only thing I'd add is we're pretty confident that with improvements in the ZK VM and basically how competitive the space has been, hopefully by the end of next year or maybe 2026, we'll have at least real-time proving down to a point where it's cost-effective for Ethereum. So that means under 12 seconds, end-to-end proofs put onto Ethereum. In the meantime, I'm quite excited about real-time solutions like space and time. So definitely that will be the unlock. Like that will be the big difference that makes it so most computation, most things done on chain can be brought into a coprocessor. In the meantime, the applications are still more focused around async use cases.
And yeah, for us at LayerEdge, like we are primarily focused on like the cost aspect of like the aggregation, because the block time on Bitcoin is like close to 10 minutes. So in that scenario, like we have not that much like time sensitivity compared to like the guys who are building on the Ethereum side. But the problem is like on the Bitcoin, like the cost of verification that's projected is pretty huge. So for that aspect, like we need like a longer time so that we can aggregate more number of protocols, and the aggregate like value of like a single protocol cost fees is lower enough that we can actually make it accessible to like most of the market.
Perfect. I think definitely like the variety of choosing real-time based proving and then the choice between if you want to compute more operations and that'll take a longer amount of time. I think having that flexibility and optimizing for those specific use case and optimizing specifically for those solutions, I think has been very critical for that. I guess we talked a little bit about use cases for these ZK coprocessors. I guess starting with you, Ayush, what do you think the main use cases for the Bitcoin side of things, Bitcoin based or settling on Bitcoin would be, and then.
So like, yeah, on the Bitcoin side, I believe like the need of the ZK processors is far higher compared to the other networks. As here, like what we actually, like, let's take the L1 network. There, like the verification is somewhat not being like possible theoretically post OPCAT. To OPCAT it's possible, it's like very expensive that it's not usable at all. So in that scenario, like the need of coprocessors is pretty high, as you can offload a lot of computation of your own tasks. Like for example, if you're creating a DEX, it's very smart that you use coprocessors for handling all the matching engine, all the order, whereas you just do the end verification on the native Bitcoin chain. That gives you like the good aspects of like basically offloading the computation, and you can also get like a smart contract, pseudo smart contract functionality, because on the Bitcoin side natively you don't have that amount of contract functionality available, which can then be enabled by like offloading a lot of computation.
For us, we really just thought about like what applications can actually afford the fees added on by ZK coprocessors and ZK proving. And naturally, we just looked at DeFi, because it's like, if you think about what are the biggest successes over the past year, it's only been DeFi apps that have been doing like 50, 100, $150 million in revenue. And then going there, a lot of those applications do want additional compute, additional state to increase their liquidity efficiency. So that's really been where we think the most amount of use cases for ZK coprocessors have been. Eventually, once ZK is cheap enough, then maybe games, NFTs, more fun things can use it. But as it stands, if you're charging even 1/10 of a cent per transaction, it's simply too much for the majority of applications.
Yeah, I mean, like, intelligent DeFi is definitely one very big category for ZK coprocessor use cases. The idea of, intelligent DeFi or data-driven DeFi is that you can dynamically change and tune DeFi protocol parameters on an individual user basis or on a protocol basis based on the historical interaction of your user or your market condition, like your proof of that using ZK. Right, so we definitely saw that as a very, very big use case, and we'll be launching our kind of a series of launch partners very soon on that category. But recently, we also have been focusing a lot on the mass adoption, the user adoption side of things. One thing I want to mention is that airdrops, right? So like airdrops, everyone knows like airdrop sucks now. It's a disappointment for both users and the project, because like for users it's black box, and for projects it's a cost center. And there's no way for you to actually build a trust-free system that continuously engage with your user and continuously kind of generate token to align with them, and in a very transparent and trust-free way. So we recently launched a new thing that's going to be a replace of the old one-off airdrop program called continuous protocol incentivization. And our first partner on this is Euro Money, which is a rising star in the stable token space. The idea is that instead of just doing one-time airdrops, we allow users to generate historical interaction with, generate proofs of their historical interaction contribution to the protocol, and then use that proof as a way to measure and calculate their contribution and generate tokens and align the incentive that way, right? So we do think token issuance and token distribution is one of the most important use cases for blockchain, and how to align that better with the community is something ZK coprocessor can power.
That was really well said. Yeah, the data-driven DeFi where protocol parameters are tuned based on the user's historical interactions is really the future for sophisticated DeFi going forward. Like again, like when I first started writing contracts in like 2020, I was just shocked that I didn't have any functions to do something like run a query, like given my user, just ask a basic question, like what's the volume of transactions their wallet has executed on chain in the last week. I was like, wait, I can't do that? I can't do that in Solidity, what? But then you run into this whole asynchronous nature, right, where the user wants to transact as fast as possible. They don't want to wait 20 blocks on Polygon or 3 blocks on Ethereum or something. They want to wait maybe 1 block to get their transaction executed, maybe 2 blocks. And so the hard part is then as you lower the cost of actual ZK proving through writing a lot of optimizations to your circuit and like using better hardware and driving down the cost of ZK proving, then you also have to pay for on-chain gas to submit the data back to the chain and usually relay it to the client via a callback function. And there's also on-chain gas for ZK for the verification of the proof on-chain. And that gas, we have no control over. The gentleman up here, we can't control that. That's the target chain charging us. And so we could write the fastest, most optimized circuits possible that cost 1/100th of a cent to run a pretty complex DeFi calculation, but if the chain charges us 8 cents to verify the proof on chain, then that usually gets handed to the end user as transaction fees. And that decreases the quality of the user's experience. And so there lies the challenge that we all have to kind of come to grips with, is like, how do you meet in the middle where maybe charge the user a little bit more for a data-driven, sophisticated DeFi experience, but not too more? And then we're unfortunately reliant on the L2s and L1s where our proofs are being verified.
Yeah, definitely different considerations related to that, and I hear that the primary use cases right now are the DeFi-driven ones, like the ones that essentially are driving the millions of dollars of transaction volumes, and then maybe like layer 2s as well are looking to essentially also come in with their own need for co-processing. So maybe like we'll see more or maybe more implementations on the different layer 2s that offer cheaper transaction verification costs, and then maybe that'll be the driver for more and more of these use cases outside of DeFi, and then or maybe like within DeFi and outside of DeFi. I guess for the final question, right before we end the panel, in terms of the long term, in terms of like adoption, where you see like a few years ahead, how what's your vision on co-processors, and how integral would it be within the blockchain ecosystem? Starting with you, Scott.
Yeah, okay, great question. We think about it like traditional app development in Web 2, where you have a API layer that contains all your business logic, your scripts for running calculations and understanding who users are. And your API layer for your app usually calls a database to get some context, that data, query results that feed into the business logic to make decisions. So if on-chain, the business logic for your DeFi protocol is a smart contract, our hope is that within the next year, 2 years, 3 years, I guess 4 years, DeFi developers start thinking that way. Hey, I'm writing a contract, my contract's gonna need data. They embed either query IDs or actual SQL statements in their smart contract, and they just build that way. Like, I build my smart contract knowing that I have expressive access to like the entire chain history and a bunch of tables about transactions, events, storage slots, updates, and user history, and I can just like embed SQL in my smart contract the same way I would if I'm writing like a Java API or a Rust API or a TypeScript API for my web app. And again, like we'll have that asynchronous problem of like we have to abstract the asynchronous nature away from the user and make it feel to them like their smart contracts just doing that, and it's not like calling an external system, which is calling an off-chain system, which is doing computation, which is oracling the result back to the on-chain relayer contract, which is forwarding to a client. I hope, though, in 4 years, that's completely abstracted, and the chains just begin integrating their own coprocessors. I've been asked so many times, like, Scott, what's the solution to the async? Well, the solution to the async is a new chain architecture where coprocessors are part of the chain itself, not this external thing that sits next to the chain and oracles the solution, oracles the answer back on.
Yeah, definitely. So, I think we firmly believe that like a coprocessor is going to lead this kind of a glue and coprocessor architecture transition in the blockchain space, where blockchain is going to look more and more like a glue of different type of coprocessors. And there's going to be a diverse set of different coprocessors. Some of them are more going to focus on very generalized compute. Some of them are going to focus on historical on-chain data access. And some of them are even going to focus on machine learning and AI workload, verifiable AI workload as well. So I think all these things is going to unfold in the next 2-3 years. But I do agree with Scott that there is a very, very big opportunity there to have essentially enshrined the coprocessor blockchain. To essentially have blockchain have a coprocessor not as an add-on or accelerate component, but an integral part of a new type of blockchain. And this is something that we are also very excited about.
Yeah, I'd say the only thing I have to add here is, we also want to talk to applications and challenge them and ask them, like, what parts of decentralization and consensus do they actually need? Like, if I'm working with a game, maybe they don't need all the benefits of consensus and decentralization. So if we want to enshrine their logic using ZK on-chain, maybe we can keep the majority of their game logic off-chain just on a server. So it's like kind of those things that we want to play around with. Like, how do we bring the internet on-chain? Most of the internet probably doesn't need a lot of the security guarantees and trust assumptions that like distributed systems and blockchains give. So can we be selective about that? I think Polymarket's a great example. Like, most things actually don't need to be on-chain. And then I think coprocessors, because of how applicable they are and how they really increase developer expressivity, they're going to be the bridge between like all the real world applications and basically what's currently on-chain.
Yeah, and I just only want to add that, like, I totally agree with the point that, like, if we see the future of, like, most of the applications built on blockchain, the coprocessors will be the part of the architecture. Because if you see, like, any kind of new use cases or the current financial use cases, you want to implement them on the blockchain, then you need a lot of heavy computations, like, or you need a lot of amount of data. So in both of the scenarios, like, the coprocessors are basically the natural fit for it. And like moving this to the core architecture is like one of the things that is like, I think, like standard for all the new projects that are building. Like, for example, like we are building a verification layer. For us it is, and like for others like AI chains, like I'm talking to, for them like calling a coprocessor is like the standard protocol. It's like not like something new that they're doing.
Awesome. I see there's a consensus of having ZK coprocessors being an integral part of different blockchains, and maybe that's something that that in the future we'll see a bit more of, and then specific to those use cases of what on-chain data, what data do you need in a trustless setting as well. Thank you everyone for joining the panel, and yeah, give a round of applause for our guests here.
I'm extra loud and enthusiastic to represent the thousands of people who are live streaming right now. Bet you didn't know there were that many people. Thanks, you guys. Really appreciate it. It was a hoot.